Section 4.5 is the multiplication rule for complements and conditional probability. I actually touched on some of this when I was lecturing over section 4.4. We did talk about the probability of at least one thing happening, didn't we? Maybe it was my other class I'm thinking about. Okay, well, we'll go over it now. Complements and the probability of at least one. At least one is equivalent to saying one or more something happened. So how would you find the complement of at least one? Remember, when we talk about complements, if this is our sample space and this is our event, everything that's outside of this event would be the complement. Everything out here would be E complement. Do y'all remember talking about that? So if my event is that I got at least one head in the 10 tosses of a coin, the complement would not be 2 heads or 3 heads, it would be no heads. The complement of getting at least one item of a particular type is that you get no items of that type. Here's an example problem. It says Topford supplies X data DVDs in lots of 50 and they have a reported defect rate of 0.5%, so that the probability of a disk being defective is 0.005. It follows then that the probability of a disk being good is 0.995. Now our question is, what is the probability of getting at least one defective disk in a lot of 50? Do you understand what it is that we're asked to find? At least one defective disk. If I were to do this head on, I would have to find the probability of getting 49 good and 1 defective. I would also have to find the probability of getting 48 good and 2 defective, because 2 defective disks is still at least 1, right? See, if I was going to approach this head on, I would have to find a whole bunch of probabilities. That'd be the probability of 49 good and 1 bad, plus, because it would be or, the probability of 48 good and 2 bad, because 2 disks being bad would still be at least 1 defective. And I would have to add up all of these probabilities down to the probability that all 50 disks are bad. It's so much easier to find the probability of the complement. The complement of at least one is none. And the reason you want to do that, or we're allowed to do that, is, remember when we said the probability of an event is equal to 1 minus the probability of the complement of the event? If this is your sample space and the probability of the sample space is equal to 1, then the probability of an event plus the probability of the complement of the event has to be 1. Because you're either in the event or you're not. The complement is the not, the negation of the event. Well, if I solve this equation for the probability of the event, I could subtract the probability of the complement from both sides, and that gives me then the probability of an event is 1 minus the probability of the complement. And that's what I'm going to use to answer this question about the disks. And what we're going to do then is find the probability of the complement. E complement is that none of the disks are defective, which means that all of the disks have to be good. So the probability of E complement is going to be, what is the probability that they're good? 0.995. And there's 50 disks, so that's 0.995 raised to the 50th. If we're rounding to 3 decimal places. So then the probability of the event is going to be 1 minus 0.778, and that's going to give us what? 0.222. So that's the probability of getting at least one bad disk in the lot of 50. Conditional probability. I know we discussed conditional probability in 4.4 about independent and dependent events. The conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. The way that we read these symbols here is the probability of B given that A has already happened. That denotes the conditional probability of event B occurring given that event A has already occurred, and it can be found by dividing the probability of events A and B both occurring by the probability that event A has occurred. This becomes our sample space because we were told that it already happened. And the way that we find the probability of an event is we look at the number of ways that event A and B can happen and divide that by the number of elements in the sample space. So the probability of A and B is going to be the number of elements in A and B divided by the number of elements in the sample space. So this right here could be rewritten as the number of elements in A and B divided by the number of elements in the sample space divided by the number of elements in A over the number of elements in the sample space. Now, do y'all remember from algebra how to simplify complex fractions? Those are when you have fractions within fractions. You take the one on top, you leave it alone, and what do you do with the one on the bottom? We flip it and multiply, right? Well, the number of elements in the sample space are going to cancel out. So what I did was I showed you that another way of coming up with this, because the sample spaces are going to be the same for both events, this conditional probability is actually equal to the number of elements in A and B divided by the number of elements in A, if you're told the number of elements in the event as opposed to a probability of an event. This and this are equivalent, and you may need to know both in order to solve problems that you're given. This right here was just the development of why those two things are equivalent. So here's an example. Refer to the table to find the probability that a subject actually uses drugs given that he or she had a positive test result. We want to find the probability that they actually use drugs given that they had a positive test result. Well, looking at the formula that we just developed, this means that we're going to look at the number of people who both use drugs and have a positive result divided by the number of people who had what? The positive result. This condition right here is the condition that you're given. So that becomes your sample space. You're already told that they had a positive test result. Now we want to know, well, what's the probability that they use drugs? So looking at this formula, then we're going to look at the number of people who use drugs and have a positive test result. So that's 44. And how many people had a positive test result? 134. And what is 44 divided by 134? 0.328. That seems low. That's the probability that a subject uses drugs given that they had a positive test result. Let's find the probability that a subject had a positive test result given that they used drugs. I'm just curious about what happens with the numbers. This is going to be the number of people who used drugs and had a positive test result divided by what? The number who used drugs, the total users. So here we go. This is still going to be 44. But what's the number of people who use drugs that admitted to using drugs? 50. So now let's find this probability. 44 divided by 50, 0.88. So the probability that somebody tested positive given that they used drugs is 0.88. Whereas the probability that somebody uses drugs given that they had a positive test is 0.32 or 33. I don't have a whole lot of confidence in these drug tests. One thing that's interesting that I'd like to point out is the probability of B given A is not the same thing as the probability of A given B. The probability of somebody using drugs just based on a positive test result is pretty low, whereas the probability of having a positive test result given that they use drugs is fairly high. These are not equal. That's one thing that you need to notice, and that's called the confusion of the inverse. It says to correctly believe that the probability of A given B and B given A are the same, or to incorrectly use one value for the other, is often called confusion of the inverse. You want to watch for this. Whatever you're given last, that's going to be your denominator, because that is your new sample space. This is your new sample space because it has already happened. The numerator here is always going to be the intersection of what it is you want to find the probability of and that event that has happened. This one still bothers me though. Let's play with this one just a little bit. Let's see, what's our totals here? The total people who tested positive out of the survey is what? 134. The total people who tested negative then would be 866. The total people who were tested is 1,000. So we had a total of 50 subjects who used drugs and 950 who did not use drugs. What is the probability of randomly selecting someone who uses? How would we find that probability? 50 over 1,000. And what's that going to be? 0.05? What's the probability that somebody tested positive? and that's 0.134. And then we said that the probability of having somebody test positive given that they use is 0.88, and the probability of somebody using given that they tested positive is 0.328. Granted, you are more likely to test positive if you use. That seems to be the highest. Let's find this out. This is another interesting one that we should look at. It's more devastating with a drug test, I think, to have a false positive, don't you think? What is the probability of a false positive? That means the probability of testing positive if you don't use. What is this probability? That's going to be positive and do not use divided by do not use. What's that number? 950. And what's 90 divided by 950? Give me a decimal. 0.0947, just under 10% that have a false positive. That's disturbing to me, because that's 10% of the people whose lives could be ruined because of the laws in our society, the rules in our society. All right, well, that wraps up section 4.5.